Thank you very much, Joe. And I want to thank you all for your patience as I struggled through Chicago traffic to make it out here. I want to tell you a little bit of a story. And that's a story about the confluence of a couple of trends that are happening, one of which is a trend that's going on in modern science, which is the movement towards big science. So that's something I got involved in, was the Slow and Digital Sky Survey. It was the first sort of big science project in astronomy, but now people look back at it and think, what were you guys worried about? We can put all that data on a hard drive, right? But things are getting bigger and bigger, more and more data is being collected, and the way we understand that data, the way we draw inferences from it, the way we teach with that data is changing. Fortunately, there are tools to help us do that. And in particular, the tools that I'm interested in are scientific visualization and the power not only of the techniques, but also the environments where we can display those visualizations to really, I think, really transform both research and education. So if I step you back in time, this is the Adler Planetarium. The first planetarium in the world was founded in Munich, Germany in 1923. So we're approaching the 100th anniversary of the planetarium. The first in the Western Hemisphere was right here in Chicago, just a few years later, 1930, at the Adler. And still, to many people, this is their vision of what a planetarium is. It's an old-fashioned machine for showing you the stars. But a revolution has happened, and a planetarium is no longer just a planetarium. It's just one of many uses that these facilities that we've created can do. Really, what we've built now are multi-purpose, flexible, immersive visualization facilities. And these facilities can deal with all kinds of sciences, not just astronomy. And these facilities can be networked together. So large groups can collaborate in a space in one large facility, but we can synchronize them across the globe for international collaboration. So what I want to start out by talking about is a little bit of the process of scientific visualization, some basic principles of how we use it for science communication, some of the things we need to keep in mind, like perceptual issues. One of the things that we're particularly interested in astronomy is teaching this concept of scale, because the scales we deal with are unimaginable. We can give you numbers, you can't understand those numbers, but we can fly you through the universe and get you a sense for what those numbers mean. And then we'll talk a little bit about immersion and the power that has for education. And there's a growing body of educational research showing that, and also for data exploration in this big data era. So this is the space I work. It's the Space Visualization Laboratory. It is a sort of hybrid space. It's a development lab that's often just for our own work to experiment with new technologies. But we also open it up to the public a couple times each day, and we invite in local scientists from all over. So University of Chicago, Northwestern, both have top 10 in the world astrophysics departments, but people come in from Argonne National Lab, and even sometimes people driving from Fermilab, although as I just demonstrated, that's difficult. That's the lab as it exists, but in my mind, this is really what I wanted to make, right? I wanted a way to play with data. So this is sort of the science fiction view of where I'd love to be sometime in the future with that lab, sort of a transparent, natural way of interacting with complex, three-dimensional data sets. The main program that happens in this lab is something called Astronomy Conversations. And there's really been a transformation in the idea of what's effective in terms of science communication. So traditionally, people tried what's now referred to as the deficit model. So that's the idea that the public doesn't understand things, so we need to explain those things to them. And if we explain them to them, then they will appreciate science more. It turns out there's a growing body of evidence that that's not true. What tends to be more effective is something what we try to practice in the lab is this dialogue model of science communication. So that's a two-way back and forth with the scientist and the public. So you're seeing now a bunch of postdocs and graduate students getting sort of introductory training. So you saw them explaining their science without using their words. Maria there was telling you about her solar dynamics simulations. You saw a young man demonstrating gravitational radiation, which was kind of amusing. In particular, this dialogue model of science communication has proven to be more effective when dealing with anti-science movements. So when we want to talk about flat eartherism or climate change denial, it's actually very, very, very hard to change people's ideas and perceptions, but lecturing at them doesn't work. And two-way communication, at least there's some hope that that can be more effective. So that's one reason why I think we're really becoming invested in thinking about ways that we can bring more of that two-way dialogue into all the programming that we do. The other aspect of what we do is not just the science communication, but it's the visualization. And I guess this is becoming an easier and easier argument, but traditionally, if you go into a physics department, people would think, well, visualization is a useful thing for showing people data, but is it really important for understanding your data? We have statistics. And what I'm demonstrating here is I'm showing you a set of data sets. These are 4 different sets of 10 points, x, y points. And what we can do is we can look at the statistics. They have the same mean. They have the same variance, each of these 4 different data sets. But if I can look at the correlations between x and y. So all the standard things statisticians do to 3 or 4 decimal places, these 4 data sets are exactly the same. And now you'll see me with my extremely slow typing attempting to plot these. Next time I take a video of myself typing, I'm going to speed up the video. You'll see that they're actually quite different. So let's take a look at that. And oh man, I should have really sped that up. Here we go. Here are the 4 different data sets. They have the same mean, they have the same variance, they have the same correlation between x and y, but they're nothing alike. And these are simple things that you find out immediately by looking at your data, but in many cases, people go right to the analysis without doing that. So visualization is important. And of course, we all know that. And the standard things like plots and graphs and histograms have been bread and butter of science. When people are suspicious, it's often about the more complex 3-dimensional visualizations. But as our data gets more complex, certainly this is how I got into science visualization, working with the Sloan Digital Sky Survey, where we had gone from sort of 2-dimensional surveys of galaxies to full 3-dimensional surveys, and I just wanted to be able to look at it. There's also a growing understanding of what's accurate and effective with visualization. So traditionally, people just make plots. I mean, maybe you guys do this. You're trying to show something, and you make a plot, and you keep changing the parameters on the plot. Let's say it's a histogram. We're binning it. We're taking different things, and we do it until it looks good, and then we stop. But you might want to know like what goes on. So people have started to look at this in detail, and one of the first studies is this Cleveland and McGill study from the 80s. And so if I go from the left to the right, what we're representing here are different graphical measures that we might use in the visualization. So the pluses represent points, the 3-dimensional, the position on a graph. Then as I go from left to right, things are less and less accurate. So we can read off position off a graph most accurately. But then things like length, things like angle, things like direction are less accurate than that, but still pretty accurate. Area is even less accurate. So if we represent area of circles or something, that's perceived less accurately by people when they try to decode that visualization. Volume, even less accurately, curvature as well. And then least accurately of all are things like hue and shading. So color is actually sort of a big problem. So when we create a visualization, it's not enough to just think about ways of encoding data to make it visual. We have to think about how that data is decoded by the viewer as well. Color is really tricky, as many of you may realize. Like this center bar is actually a solid color, believe it or not. If I take away the background, so we're fooled by the background there. Of course, we know this. Do you remember the dress? Yeah, right? What color is that dress? I can't even remember what color the dress was. Gold and white or black and blue. Nobody knows what color the dress is. And it has to do with all the calculations that our brain have built in to adjust for lighting and contrast and color when we think about what a color is. This is a similar example. Those squares labeled A and B are actually exactly the same shade, but they don't seem that way to the human eye. And this comes into play in some of the visualizations we use in science. So this is a map. Does anyone know what the map is of? Joe knows, I'm not surprised. What? Yes, the cosmic microwave background. And I've given this plot to astronomy departments, and I'll just show a little tiny piece of it and ask people what it is, and everybody knows what it is, even though it's just blobs. And they know it is because they recognize this color map as being the color map that was used to represent this cosmic microwave background radiation, which is really relic radiation that's left over from the Big Bang. And those little blotches are little tiny spots. Some are hotter, some are colder, that actually seeded the structure that led to our entire universe. So it's important stuff. But when you look at it, what are the parts that stick out to you? Well, do you see like yellow's really bright? The blue kind of pushes in the background. Some of that's the way we interpret color. There's a growing movement to really stop scientists who really love to map everything with these rainbow color maps and to get them to stop, because they're not effective at all. They're not effective in particular because our eye perceives some colors more strongly than others. So here is another one of these Jupyter notebooks. I've mapped out this concept of luminance. So that's how our eyes perceive things. It takes into account the fact that we perceive green stronger than blue, for example. And you can see these kind of plots have these little peaks. So, and it depends. There are different rainbow color maps. Some are worse than the other, but those peaks pop out in the visualization, and it may cause us to see features that aren't really there, or to miss features that are really there. What we often want to do when we're measuring a single scale is to use what's called a perceptually uniform color map. And this is an example of one of those. It's also a nice one. It tends to avoid some of the major color bonders. If I think about the CMB, actually that's an interesting case, but in that case, really what we have is an initial universe that was smooth and homogeneous with slight variations, and we wanted to see the positive variations, the hotter spots and the colder spots. And in that case, when you have a mean and you want to measure divergence from the mean, this type of color map, a diverging color map, is more useful. And so that kind of color map is much more useful for measuring something like the cosmic microwave background. And I kind of forgot my lead into the joke, but I was going to say, all right, so it might make a difference. Some color maps might be better than others, but really, is a bad color map going to kill anyone? And the answer is yes. Bad color maps do kill people. So here's an example from medical imaging. And there are a set of visualizations here, but the important one to look at initially is this one in the lower left corner. So you have a three-dimensional rendering of this artery, and you're mapping on that some sort of measure of stress that comes out of some medical imaging, and you're trying to find weak spots in the aorta. So the one on the lower left that's labeled C is the kind of visualization that technicians were looking at and doctors were looking at to do this diagnosis. And the visualization scientists looked at their software, and they actually performed two interventions. One was to use that same three-dimensional rendering, but to put it on a diverging color map like we just talked about, and they actually tested a whole bunch of different color maps. And the other was to get rid of that third dimension entirely and to unwrap these things and put them flat. And so they did two things. One, they asked all of the doctors which one they liked better, which was more effective. And by a very, very large majority, the doctors said what they were doing before was much better. They loved the rainbow color maps on their 3D models. But then looked at how accurately they were finding these weak spots, and they increased from only detecting 62%, which is a little scary, to 91%. So that's kind of the power of a good visualization. And now let's go back to the cosmic microwave background. Really, we're measuring this one-dimensional thing. We don't really have color, so we could just treat it as grayscale. But since it's really this diverging map, maybe a diverging color map is more effective. And this is actually the one that's been done by the team that's measured a more accurate. You see there's more detail in there now. And because this was a new satellite that came in later and has the most accurate map of this Big Bang radiation we have today. When we are presenting science to the public, there are additional considerations than when we're just communicating among scientists. And color provides some really good examples of that. So has anyone ever been to a bathroom? No, sorry, this is a bad joke. But when you go to the bathroom, hopefully you also visit the faucet. And when you go to the faucet, you'll see there is a hot and a cold. And what color is hot? Red. And blue is cold. But are hot things red or blue? Really, hot things are blue and cool things are red, right? So we've built in this misconception about temperature. The art teachers are pushing it, right? It's like it's ingrained in our society. And when we want to present an image in astronomy, so this is an example from this project called Aesthetics in Astronomy by colleagues of mine who work with the Chandra X-ray Space Telescope. In that case, they're not looking at things in red, green, and blue. They're not taking color images. They're looking at different wavelengths of X-rays and making color images out of that. And the traditional way you do that is you take the highest energy X-rays, you make them blue, and you take the lowest energy X-rays, and you make them red, and you build a three-color image, like the one we have on the top. However, when they started to ask people about them, and like, where's the hot gas and where's the cool gas, people were misunderstanding that. So they actually tried inverting those colors, which you see on the bottom, and people were actually understanding the images better. Fortunately, now I think it's becoming more and more confusing about what best to do. In the lab, I often ask people, because I'll talk about stars, I'm like, what's hotter, a red star and a blue star? And then when I asked that 5 years ago, most people get it wrong. Now I think most people get it right. So maybe the art teachers are getting better at it, or the science teachers or somebody. Here's another example about color in the public. So this is, you're looking at 3 different visualizations that we did actually as part of a sky show that we produced at the Adler Planetarium. And what you're looking at is the formation of structure in the universe. We're seeing on very large scales matter collapsing into galaxies and clusters of galaxies and superclusters of galaxies. That blue image on the left was initially how we visualized it, and this is actually an interesting visualization because where the matter is where galaxies are, and we transition to a real map of galaxies. We initially, and then actually what was in the show was that blue visualization. But one thing initially I was noticing is that it was actually really difficult to make out some of the fine structure in that black on blue, and that came from the fact that actually our eye doesn't perceive blue very well. One thing that early astronomers did when they were trying to figure out the shapes of galaxies, so classifying galaxy shapes, is they would do it not on the image itself, but on the negative of that image. And so that was sort of that inspiration for inverting those images. So we were seeing this sort of black on white image, right? Where the material was the dark stuff and empty space was the white stuff. There's another interesting thing that initially I was just doing this to see the structure of the universe better. But the reality is, that structure that we're looking at is structure not in matter. It was actually structure in dark matter. In this simulation, we didn't simulate regular matter at all. It was simulation only of dark matter, because really most of the universe is dark matter. And that's really what matters. we had a young woman who was working on her PhD at the time. This formed a part of her thesis about the public's understanding of cosmology. And she would interview people after our show. And she would ask them, where's the dark matter? And people would say it was the stuff in between the galaxies because, it's dark. And so that led to this study where we took three different renderings of the visualization. And you can't really read the markings by the graphs, but I'll explain what the colors mean. So we looked at this blue one, this kind of peach one, and this inversion, and asked a bunch of questions about the dark matter. And of course, people, you tell them that, that what's dark matter and what's not, but really people expect dark matter to be dark because that's its name. So what happened was, in the way we were showing the visualization, that blue way, when asked these questions, the red is the important part of the pie. That's the number of people who answered most of the questions correctly. And we went from 25% correctly to, in the inversion, 75% of the people answering the correctly. So that choice of color had a dramatic effect on people's understanding of this visualization. And as a scientist, you kind of forget, well, we always draw dark matter as blue. You forget that people actually expect dark matter to be dark. And one of the nice things about the planetarium field is there's good collaboration. So we sort of learned that from our failures and some of the studies we did here. Later on, when I was talking with my colleagues at the American Museum of Natural History, they were producing a show called Dark Universe, which has this incredible simulation of the formation of structure of the universe. And they actually, because of that study, they did that inversion of the color. So the dark matter is dark. And then at the centers of the most dense knots of dark matter, that's where galaxies light up. And so they drew that as yellow. So in the last part of my talk, I want to talk a little bit about this evolution of the planetarium and what the potential behind what a planetarium is as we enter our second 100 years. What is the role of a planetarium? So, as I was said at the beginning, I think the answer is that what we've really built in cities all around the world are these world-class, immersive, big data visualization facilities. In many cases, these facilities are superior in capabilities to those that exist at major research universities and national research labs. So here's an example of some of the academic solutions for immersion, large group immersion. The one in the middle is probably the most common. It's something called a cave, very expensive, can only fit a few people at the time. You have projections on 4 walls, or in some cases on all 6 walls, and people wear tracked stereoscopic goggles. The next generation of that, the Cave 2, is a spectacular facility. There's one nearby at the Electronics Visualization Laboratory at UIC, 70-some displays with passive stereo. It really blows me away. It's a more than $1 million investment. On the left is one that one of my colleagues built. He actually went from working in planetariums to becoming an oceanographer, and then so he now goes out on these expeditions, sending down little robots down the bottom of the ocean and mapping out the seafloor. And he wanted to use some of the planetarium tech to understand his data. But when he started doing it, all of his colleagues would complain. They're like, why are we looking up? Usually we're used to looking down. So he took the planetarium and flipped it upside down, and he built this thing. But the power of these kinds of spaces is that they can put you in a place. So here I am with a colleague who studies this place called Jantar Mantar. It's a 17th century observatory, actually a set of 17th century observatories in India, the most spectacular of which is in Jaipur. You should totally go next time you're there. And when we put this in the planetarium, these 360 imagery he took, It's actually like we're in that space. And that power can have a positive effect on education. There is a decent amount of research, and I think also as the technology improves, there's a need for more and more of this research that really is working with this sort of highest level of technology. So some of this is a little bit dated, but I have a good friend at the Denver Museum of Nature and Science who's worked with the local university there. And what they've done is they've taken classes and they've taught them in different ways. So they've broken up the astronomy class. Some get traditional classroom instruction. Some get traditional classroom instruction, but using some of the 3D visualization software we use in the planetarium. And some actually go in the planetarium and see it that way. And then they take pre and post tests, and then they go back later and see how they've retained that knowledge. The big takeaway from this is whether or not people learn more or not in a planetarium really depends on the nature of that content. So it seems like some types of content really benefit from having that wider field of view. In particular, with introductory astronomy, things like understanding coordinate systems or the seasons. And in other topics, it's not as obvious. We did a study about, not about the field of view, but about stereoscopic vision, this NSF study. And what we did is we produced some 3D movies. We showed them to people in the lab, and they did a series of tasks. We decoded their spatial perception skills. We even tracked them on an iPad to see when they're understanding things. If they tilted the iPad, we stored all that accelerometer data to see how they looked at things. And we had them draw images of what they learned. One of the things we did was a little video about the 3D structure of the galaxy. It's sort of an interesting topic because if you think about it, and this is actually an introduction where we deal with some of the historical understanding of the 3D structure of a galaxy, and this is using some of imagery from some of the historic collections we have at the Adler Planetarium. This was a pretty fanciful model by a man in like 1750. But so much of what we do in astronomy is really taking essentially two-dimensional information, because the universe is very far away, and abstracting that to a three-dimensional view. In particular, our own Milky Way galaxy, it's hard to know what our own galaxy looks like because we're stuck in the middle of it. So that was kind of the story about how we go from 2D to 3D, and we tested if the 3D, the stereoscopic vision, helped people understand that story. And it's interesting. If you look at the results here and the graphs, so again, you can't read, I apologize, the text. You can watch the graphs. What we found is that people watching it in 2D and 3D had a significant learning gain, and they had almost exactly the same learning gain, statistically insignificant. But then when we went back 6 months later and asked people, what we found is half the learning gain from the people who watched it in 2D was lost. Where actually there was very little loss for people who saw it in 3D. So there's something about that environment, that stereoscopic vision, that made things more memorable. It turns out, and that's what this unreadable graph is on the left, is that people have done similar studies in a planetarium and found a similar thing. Actually, the most significant thing seems to be in terms of retention. And so I think there's really something here, something about that power of the planetarium. And some of it's just the nature of that experience. We're going to sort of fly out from Fermilab and out through our solar system to sort of show you sort of the kinds of things we do in a planetarium. And I mentioned before this concept of scale and how challenging that is. But really what's important is not understanding the numbers, it's understanding the hierarchy of the universe. As we go through past the moon to see our solar system, through the local stars, to our galaxy, the Milky Way, through the universe of galaxies. And this map is actually that map that we started out in the introduction telling you that I worked on 20 years ago when I came to Chicago, which was building the first really large three-dimensional map of our universe. This is a map of 1 million galaxies. So I can give you those numbers, and it's really hard to grasp, but it's not that hard to watch that video. When we talk about scale in astronomy, there are actually a couple of scale comes in a lot of ways. One way it comes in is, if you think about those Hubble images, right? We all see these beautiful Hubble images, but we don't have them in context. One of the things we've been playing with, we have a show now, the planetarium, that plays with this idea, is trying to understand angular scale. And so this is using software called Worldwide Telescope. It's freely available. It was initially a project from Microsoft Research, but it's now an open source project and managed by the American Astronomical Society. And what it builds is this platform for actually layering and displaying essentially all the world's astronomical information. If people make their information available on the internet and distribute it, you can go out and grab all these sources, and then you can layer in very accurately on top all these different scales. So we've just zoomed in to a Hubble Space Telescope image. This image is about 1 minute of arc across. So the first time we stopped at 1 second of arc, that's about the width of your finger at arm's length. Divide that into 60, that's 1 minute. And then we see in that Hubble image some young stars. We can't see what's going on at the center of the star through optical light, but using this radio image that comes from the ALMA radio telescope array in Chile, we can actually zoom in and we can see structure in a disk that's forming around that star. That structure is happening because planets are beginning to form. This is the first time we're able to see that in that image. And if we zoom in even farther, using an image from the VLA, the very large array, we actually see this clump, which is a clump of dust 3 times the mass of the Earth that's in the process of becoming a planet. This is about a 1/10 of a second of arc across. So I mentioned right at the beginning that, if you go to physics department, many people would poo-poo the value of visualization. And, maybe they were right back in the day, but the day is changing. In particular, what's changing is just the quantities of data that we're dealing with. So on the bottom are some of these really big data projects in astronomy. So on the left is an in-construction photo of a project that we're involved with at the Adler Planetarium called the Large Synoptic Survey Telescope. Right now, big telescopes look at tiny fractions of the sky. We saw that with the zoom in. If the Hubble Space Telescope were to observe the entire sky, sounds like a good project, make it do it, it would take it about 3 million years. But with new technology, we can do that. So this is a telescope with a wide field of view, with a 3 billion pixel camera that's going to scan the sky every 3 nights. We'll see a little bit more about that in a second. In the middle is a new satellite called Gaia. They're about to release their data set of the positions of stars. Before Gaia, we knew the 3D positions of about 100,000 stars. In a month, we'll know 3D positions for 1 billion, almost 2 billion, 1.5 billion stars. And that's freaking me out because our favorite thing to do in the planetarium is fly through the stars, but if I load this into my graphics card, the whole system will come to a crash. We don't know how to do it. We can't deal with 1 billion things. We can deal with 10 million things. And those projects, even as big as they are in terms of data, are dwarfed by the one on the right, which is a rendering of a radio telescope array that's being built in South Africa called the Square Kilometer Array. And because of its nature, the data volumes in radio astronomy are vast. And the argument I like to make is that as data sets get bigger, visualization starts to win out as a data analysis tool. And this is the argument why. Many of the techniques we like to use to statistically understand data scale very poorly with the number of objects. Depends exactly, but a standard analysis I would do for clustering of galaxies scales like the square of the number of objects. visualization scales much better. It tends to scale roughly linear with the number of objects. So that's what this equation is representing. V goes like O is the big O notation. So the time it takes to do a visualization V scales like N, which is the number of objects, or maybe also P, the number of pixels. So I have a bigger display, I need to render more. But the reality is that we've been making bigger and bigger displays. At some point we stop because we can only see so much. We have, at the Adler planetarium, it's 8,000 pixels across on our big display, so it's quite large. So it scales linearly, and linear scaling is great. But if we're smart, it can scale even better than that. It could scale like the log of the number of particles. And that's because you don't actually need to access all the data to make a visualization. You only need to access information in a way to make something that is perceptually accurate. So for instance, if I'm looking at stars, and I'm looking at stars very far away, I don't care about them. I care about clusters of stars. And I'll show one cluster of stars as a point. And that kind of intelligence, which has to go in how you create the visualization, how you store the data, and how you access the data. So it makes the process much more difficult, but it allows you to get this really nice scaling to big data. This is drone footage of this project, the Large Synoptic Survey Telescope. So this is really the next big exciting thing for the next decade of astronomy. It's going to image 20 billion galaxies, 17 billion stars every year. But what the really exciting thing is that for the first time it's opening up this time domain in astronomy. By going back and measuring things night after night after night, we're finding things that change. And they expect to find 10 million things that change every night. And when we encounter one with no more than 90 seconds, we want to identify that object, process the data, figure out what kind of object it's likely to be, send out an alert to the astronomical community so people can track it down with another telescope. All that's supposed to happen within 90 seconds. So that's where big science is going. So I mentioned some big data problems in observational astronomy, but in the computational realm, they've been dealing with that for a long time. So I mentioned that log n scaling. This is sort of representing how you can do that. So this is a visualization we did of the large-scale structure of the universe. But what I'm showing here is a certain path. So when we were looking at that visualization, we flew down that green tube in the middle. And so I only needed the most accurate data in the green tube. And in the red tube, I could look at data that was half as accurate. And the blue tube, half as accurate as that. And so this staggered level of detail is what allows you to deal with these really vast data sizes. Here's an example from an even bigger simulation. So they've been dealing with the big data problem in computational physics for a really long time. This is a simulation called the dark sky simulation. That circle is representing a volume of space equal to our observable universe. So we're actually creating simulations that are bigger than our entire observable universe. And in particular, what made this simulation, there are lots of simulations like that. Some of the largest actually in the world have been done at Argonne National Lab, the Blue Water supercomputer there. What made this simulation interesting was they thought really intelligently about how to store that data. So what we just wrote out was how the data was stored on disk according to the space-filling curve. And what that means is if I'm looking for a little piece of that data, I can go to it and find it very accurately rather than having to read in the entire data set. That's just a little cute advertisement. And so here's an example. Unfortunately, they used to have a Twitter bot, which was really great, where you could tweet this simulation. It would render a visualization for you. I think it's not working now. This is an app, and you can try this on your phone. You can 3D visualize a piece of that giant simulation, this entire universe simulation. What you give it is each of these little clumps in the simulation gets a number. And if you send it a number, it'll visualize that region of the simulation. And it can do that really fast. So if you were to try this right now, you'd wait a few seconds. What's happening behind the scenes is that it's accessing data from a 32 terabyte file, pulling out the piece it needs and bringing it back and rendering it in your phone. And you can do that just because you're smart about how you pre-process the data. So that's the kind of intelligence we need to do visualization in this big data era. All right, so let's finish up by talking about planetariums. Like I said, a planetarium is not just a planetarium. It's an immersive data visualization facility. Can use all kinds of science. Here's some images from a project I was involved in called Neurodome, where I actually took neuroscience data and visualized in the planetarium. It was super fun. On the left, actually both these are visualizations of something called diffusion tensor imaging, which maps out pathways in the dome. But in particular, what that data actually is actually a three-dimensional tensor field, which is something we don't deal with a lot in astronomy. So it's kind of a challenge to figure out how to do that. On the right, we visualized it in a technique which we did not show to anyone because they look like little weird pills, but it was kind of fun. It's something called superquadric tensor glyphs. It's another interesting project called Seismic Dome, where they visualized seismology, simulations, and data sets in the planetarium. But the great part was actually sort of turning the dome inside out, so the dome now became the surface of the sphere, and we were seeing what was going on interior to that. They also combined this with some really spectacular sonifications, which pretty mind-blowing. Back to the Adler. Back in 1930, when we were founded, Max Adler wrote that with the aid of the planetarium and astronomical museum, science may be advanced. That was a very grand statement. It was a complete lie, right? Because this was like 1930. Hubble had just figured out the scale of the universe. We were unlocking the secrets of the atom. And then we built this machine to tell you about the constellations and tell you about Perseus and Andromeda. We weren't advancing science. I mean, it was a wonderful thing. And actually, it did advance science in the sense that many, many generations of important scientists were inspired by what they saw there. But we weren't doing cutting-edge research. I mean, that wasn't really possible. But I think now it is possible to advance science in a planetarium. And one of the things we've been doing with the International Planetarium Society is to really push this new use of a planetarium. And we've been encouraging planetaria around the world to make their facilities available to researchers, perhaps, and communities in general, after hours, perhaps, as a visualization facility. So no longer are these just to tell you SkyShows, but maybe this is a place where people can go in and examine their data sets and gain physical insight. As part of that invitation, there was this column in Nature which really reached out to the scientific community, inviting them to collaborate with their local planetariums. And that quote there, which you can see in bold, planetariums are, for the first time, able to give back to the scientific world. And you see also the tagline at the front was conveying almost a little bit of frustration, and my friend Tom tends to get frustrated, so I'm not surprised that came out. But he said, they're useful for all types of education. They can display all types of data if only scientists thought to use them. Like the frustration about really taking advantage of that possibility. And it's not surprising, because what's happened is we built better and better facilities to do a better job of what we had been doing. And without really thinking about it, we created something with much more potential than that. Here's an interesting experiment, and I think it's the premier experiment in trying to do that. It's happening at the Iziko Museum in Cape Town, South Africa. Last summer, they opened up a new planetarium and digital dome. There I am with Tom Jarrett, one of the scientists who was involved in the project at the University of Cape Town, astronomer. At the opening, you see us with our sort of ugly neckwear. Whose do you think is more garish? It's hard to tell. I guess it's a tie. There you see Tom looking at his data, some of his galaxy survey data. I was back there in December when we had an event called Dot Astronomy, which is a really cool event that happens in the astronomy community that brings together sort of astronomy and the web. And we had a hack day in there, and you see some scenes of some of the visualizations we did in the hack day. This is looking at citizen science data of the classifications of galaxies in the planetarium. One of the initiatives we've been doing with the IPS is meant to deal with the fact that astronomy is such a rapidly changing field, and discoveries are happening so quickly, and how do we get that information out of the public? So we've invented this new standard, and that standard tries to make it possible to go from discovery to display in a planetarium almost instantly. So that's like web stuff that you don't need to know what's happening behind the scenes, but what it enables you to do, and now we're looking at a screenshot from, this is one example of the control interface that the person behind the scenes has. And what they will do is they can actually go and refresh this data to Dome feed, and they'll see every day new things that pop up. They can click on it, they can download it, and they can display these discoveries when they happen. So perhaps you remember the big TRAPPIST-1 announcement about this exoplanet system with 3, possibly 4 planets in the habitable zone. That press release went out in the morning. Right after the press release, you could go into your planetarium software, click download, display a visualization of what that planet we imagine it might look like. And that's the kind of thing we're trying to move towards. At the Adler, we've been playing with how we create SkyShows. We're trying to create a new style for shows, one that's less voice of God. From the dawn of time, man has looked to the stars and wondered. And a little bit more that sort of dialogue model of science communication. So we call this sort of data visualization-driven storytelling. Our most recent show, Planet 9, is I think a good example of that. Planet 9 is about this story about this hypothetical 9th planet. The argument for why we think a planet might be out there that we haven't discovered yet, a planet very far away from the sun, is actually somewhat complex. We try to make that complex argument using the visuals. Let me give you an example for one of the more complex things in the show. So this is based on some of the research of Mike Brown at Caltech, and we started off with, this was his graph to explain the thing that we were looking at. And what he was trying to describe in this graph is that there's an object that he studies called Haumea. It's a fascinating world that's kind of football-shaped and spinning very fast. And this is evidence that we think Haumea, actually the reason why it's spinning so fast is because it originated in a collision in the early solar system. And what the plot shows, if you look at the open circles, these are things that look like Haumea. They have similar spectra. They're very icy. Haumea is unusually icy. And you see they're kind of clustered together in this 3-dimensional space, and that 3-dimensional space is a space of orbital parameters. So it's sort of a complex space. So we played around with showing what that looks like in 3 dimensions. One of the challenges is that clustering in orbital parameters doesn't really show up in a clustering in 3-dimensional space. And part of the reason, so the green object is Haumea. These purple objects are objects that look like Haumea. And these things are all beyond the orbit of Neptune in a region called the Kuiper Belt. So all these other objects are all the other things in the Kuiper Belt. And here are all the orbits of all the other things in the Kuiper Belt. But you can see, if you start to look at it, that there is some similarity in these orbits. They all are kind of tilted out of the plane by the same amount. They all have about roughly the same shape. Actually, if you look in detail, They all are about the same distance from the sun. But what's happened is that over the billions of years, the history of the solar system, their orbits have gotten scrambled. One of the things we could do with the visualization is actually say, all right, well, let's only talk about those orbital parameters that matter in that visualization, and let's unscramble the orbits. Let's undo the effects of millions of years of evolution, billions of years of evolution in the solar system. So now we're going to unwind those orbits, and we see that they actually form this very tight bundle. And that's really the evidence that they had all come from the same place when the proto-Haumea got smashed 4 billion years ago. So that's the kind of way in which we sort of make these arguments through visualization. One of the other things that we've been doing is something called dome casting. And this is really trying to connect the global community of planetaria. And what we can do with this technology is similar to stuff that's been used in video games forever, right? When you can play these multiplayer games. I can play Halo with, all right, I've just dated myself by saying that. But imagine I can play Halo with somebody like across the globe. And so that's what we do in the planetarium. I can control a planetarium, and I can control planetaria around the world. And we've been doing this in a series of lectures where, typically we connect to between 15 to 20 different places all around the world: Europe, Africa, South America. We've also started streaming that to, now that people have immersive devices in their home, is actually streaming 360 videos from the lecture that can go directly to YouTube 360, be picked up on an Oculus Rift or even a Google Cardboard headset. So what you're looking at here is from one of our lectures, a demonstration of how gravitational radiation warps space-time. But you're seeing that 360 view, which is kind of trippy. And one of the cool things about being able to reach people in their home is that we can have people attend these lectures who are not able to come to the planetarium. So this is a young woman at the Chicago Children's Hospital who was able to watch that lecture live from her hospital bed. At the same time that was going on, here's a group of people in a museum in New Zealand watching the same lecture about exoplanets. I'm just going to finish with a little about those lectures.
My name is Lisa Kaltenegger. I'm the director of the Carl Sagan Institute at Cornell. And today we are at the Adler Planetarium for a special planetarium show that we developed with the team here to tell exactly that story, where we stand right now in the search for life and what's the next steps in our immediate future. In the last couple of years, we have found these worlds that orbit alien suns. So not ours, but another sun. And the question if any of these worlds actually have life is one I think that everyone harbors and that connects the world. And so cutting edge science connects with this curiosity that everybody harbors. And that's what we're talking about today. This presentation is completely different than anything I've done before. What I love about the Kavli Foundation Planetarium show is that it gives you time to interact with visual artists that provide these graphics in this immersive planetarium environment. And as a scientist, you get to tweak to make it the most realistic. And I personally feel it actually takes you there. Having this ability to work with the designers, to tell the story that you see in your mind's eye, and then see it in 3D all around you. That was crazy, amazing, fascinating, and most of it was also fun. So thank you to the Kavli Foundation for doing this. I loved seeing this on the big screen.
I hope that it gives a little bit of idea of, I think, where things are moving with immersive technology. I would really encourage everybody to, there's a link to my website, but feel free to reach out to me if you have questions or want to discuss anything we talked about today. All right, well, thank you all so much.